Pick up a single grain of sand. Hold it between your finger and thumb. That grain is the sun. Everything you know as large, as powerful, as the center of the world you live in becomes, in the model we are about to build, a particle small enough to lose in the folds of a shirt. And in this model, the nearest other star is another grain of sand, and that second grain is sitting 7 kilometres away from the first. 7 kilometres. An hour's walk. That is the nearest neighbour to the sun, in a scale model where the sun is a grain of sand. Everything in between, all 7 kilometres of it, is almost perfectly empty. That is the first thing this video is about. And over the next 1 hour and 45 minutes, we are going to walk all the way out to the edge of the observable universe at this same scale, measuring every step. And you will see, by the time we are done, why the universe is the kind of place it is. Why it is so quiet. Why we have not heard from anyone else. Why the distances between things are not the kind of distances human intuition was built to handle. If this has you hooked, subscribe to the channel so you don't miss what comes next, because this story is just getting started. Drop a comment below. I want to know where in the world you're watching from, what time it is where you are, and your honest take on this. If the sun is a grain of sand, and the nearest star is another grain 7 kilometres away, what does that tell you about the universe? Tell me what you think. Now, settle in because we have a lot to unpack. Part 1. Establishing the scale. The sun has a radius of about 700,000 kilometres. That is a real object, a real number. If you wanted to put a line of Earths across the face of the sun from one side to the other, you would need 109 of them, stretched along the diameter to reach from edge to edge. The sun is large. Not the largest star in the galaxy, not by a long way, but large by the standards of anything a human being will ever encounter directly. It is the largest object in our neighbourhood. Everything we are about to talk about will be scaled relative to it. For the scale model, we shrink the sun down to the size of a single grain of sand. Not a big grain, a medium-sized grain, the kind you might find on a beach about 0.5 millimetre across. 0.5 millimetre. That is our sun, for the duration of this model. Everything else in the universe, every planet, every star, every galaxy, every structure at any scale will be shrunk by the same factor. The ratio between the real sun and our grain of sand sun is about 1.4 billion to 1. That ratio, that compression, is the rule we will apply to every distance, every size, every number for the rest of the walk. Why a grain of sand? Because a grain of sand is something you can hold in your hand, something your brain knows how to locate in space, something your body can feel when you pick it up. A grain of sand is a unit of experience, and by choosing a grain of sand as the stand-in for the sun, we convert the rest of the universe into distances that can be measured with ordinary human tools: meters, kilometers, walking distances, driving distances. Distances you can compare to the size of your hometown, the width of your country, the shape of your continent. The compression factor is the whole trick. Once you accept that the sun is a grain of sand, everything else in the universe follows automatically. The Earth becomes a dust mote. The moon becomes a smaller dust mote, Jupiter becomes a barely visible pebble, Neptune becomes slightly larger than a grain of table salt. The distances between these objects become measurable in human units, and the nearest star, which was previously an unimaginable number of trillions of kilometres away, becomes something you can walk to in an afternoon. Not really, of course. In the real universe, you cannot walk to the nearest star. You cannot get there in any human lifetime. But in the model, yes. The model makes the universe local, in a way, while still preserving the honest ratios between the things inside it. And once you have the ratios right, you can start to feel, in a way that the raw numbers do not allow, what the shape of the universe actually is, how spread out it is, how empty it is, how far apart its bright objects are, how staggering the gaps between the bright objects become when you zoom out toward the large scales. The scale model is not a toy, it is a translation, a way of rendering the universe into a language your body already knows how to read. So, hold the grain of sand. Put it in the middle of an empty table. The sun is at the center of the room. The rest of the universe is the room around it, and the street beyond the room, and the neighborhood beyond the street, and the country beyond the neighborhood, and the continent beyond the country, and then out into distances that, even at grain of sand scale, exceed any continent on Earth. We are going to walk outward, and we are going to measure every step. And at the end of the walk, you will understand why, when we say the universe is large, we are not exaggerating. Even at grain of sand scale, the real size of the universe will still exceed, by orders of magnitude, any human experience of distance. Part 2. The planets at sand scale. We start at the grain of sand, the sun, in the center of the model. Around it, the planets orbit. Each one shrinks by the same factor. What are they, at our scale? Mercury, the innermost planet, becomes a speck so small that it is barely visible without magnification. Its radius, scaled by the same factor that makes the sun a grain of sand, works out to about 1/100th of a millimeter. 1/100th of a millimeter. That is smaller than the dot over a printed letter I. At this scale, Mercury is essentially a dust particle. Its orbital distance from the Sun at its average separation works out to be about 41 meters. 41 meters. That is the length of a swimming pool. Mercury orbits the grain of sand Sun at a distance of about a pool length. Venus, the second planet, is slightly larger than Mercury and further out. Scale down, Venus becomes a dust particle about 3/100ths of a millimeter across, orbiting at about 77 meters from the grain of sand Sun. 77 meters. That is roughly the distance across a small parking lot. Venus is a barely visible speck about a parking lot's width away from the Sun. Earth next. Our home. The planet on which I assume you are sitting while you listen to this. At scale, Earth is a dust particle about 3/100ths of a millimeter in radius, a tiny bit of nothing. And its orbital distance from the Sun, which in the real universe is about 150 million kilometres, becomes, at the grain of sand scale, 107 meters. 107 meters. Roughly the length of a football field. If the sun is a grain of sand on your kitchen table, the Earth is a fleck of dust you probably cannot see, orbiting at a distance of about a football field away from the grain. Let that land for a second. A grain of sand at the center of a football field and a dust mote you cannot see, drifting around it at the perimeter of the field every 365 days. That is in the honest ratios of the real solar system, where our planet lives in relation to our star. That is the home we are all in, and the rest of the planets keep going outward. Mars is another dust mote, slightly smaller than Earth, at about 160 meters from the grain of sand Sun. Jupiter, The largest planet scales down to a particle about 1/3 of a millimetre across, roughly the size of the grain of sand that represents the Sun itself, but slightly smaller, and it orbits at about 550 metres from the centre. 550 metres, a third of a mile. Saturn, scaled similarly, sits at about 1 kilometre from the grain of sand Sun. Uranus at 2 kilometres. Neptune, the outermost major planet, at about 3 kilometres from the Sun in our scale model. 3 kilometres. That is a distance you can walk in half an hour at a leisurely pace. From the grain of sand, Sun on your kitchen table, Neptune, the farthest planet, is about 3 kilometres away. Out of your house, down the street, across the neighbourhood, past a few blocks of other houses, 3 kilometres. That is the radius of the planetary part of the solar system at our chosen scale, and all of that volume from the grain of sand, Sun at the centre, to Neptune at the outer edge is mostly empty. The dust motes of the planets are so far apart from each other that at grain of sand scale, the space between any two of them is effectively vacuum, punctuated by the very occasional bit of orbital dust. Between Earth and Mars, a distance of about 60 metres in the model, there is nothing substantial. Between Mars and Jupiter, 390 metres, nothing except the asteroid belt, which at this scale is a very thin scattering of grains of sand and smaller particles spread across a volume so large that any probe crossing the belt would almost certainly encounter nothing. The solar system at grain of sand scale is mostly empty space. A grain of sand at the centre, some dust motes, a larger grain at Jupiter's orbit, some more grains at Saturn, Uranus, Neptune, and huge intervals of nothing between them. A sparse, mostly empty region measuring a few kilometres across, scattered with a handful of small particles. That is the scaled solar system. That is the region that, when you stop compressing it, actually contains everything we call home. Part 3. Voyager's place in the model. The Voyager spacecraft, 2 of them, were launched in 1977 and are now the farthest human-made objects from Earth. Voyager 1, the faster of the 2, is currently at a distance of about 250 astronomical units from the Sun. That is well beyond Neptune. That is out in the region where the Sun's solar wind begins to give way to the interstellar medium. That is the heliopause, the boundary of the Sun's bubble. At grain of sand scale, where does Voyager sit? The math is simple. 250 times the Earth-Sun distance, scaled by our compression factor, works out to about 26 kilometres. 26 kilometres from the grain of sand Sun. That is a serious distance in human terms. That is the width of a modest city. If your grain of sand Sun is on your kitchen table in a house near the centre of town, Voyager 1, the fastest human-made object ever built, launched nearly 50 years ago and continuously moving away from the Sun at 17 kilometres per second, is now at a distance of about 26 kilometres from your kitchen, out past the city limits, into the suburbs or the farmland beyond. 26 kilometres in 49 years of flight, at the fastest speed a human-made spacecraft has ever reached. Think about that. The fastest thing we have ever built, launched almost half a century ago, has not yet reached at grain of sand scale the edge of a small city. And Voyager, as impressive as its journey has been, is nowhere near the nearest star. We have not yet talked about the nearest star. We are still inside the Sun's own gravitational domain. The Sun, at grain of sand scale, has an outer boundary that extends far beyond Voyager. The Oort cloud, the outermost shell of icy objects still orbiting the Sun, extends out to roughly 1 light-year from the Sun itself, 1 light year. At our scale, 1 light year compresses to about 67 kilometres. 67 kilometres. That is the edge of the Sun's domain, the outermost reach of anything that is still gravitationally part of our solar system. 67 kilometres. Far beyond any city, out into the countryside, out to the next town, beyond the suburbs, beyond the farmland, into the regions where the roads get narrower and the houses get sparser. And everything inside that 67-kilometre sphere, from the grain of sand sun at the centre to the outermost Oort cloud comets at the edge, is, gravitationally, the solar system. Everything, including the planets at their 3-kilometre radius, including Voyager at 26 kilometres, including the most distant known Sedna-like objects further out. All of it embedded in a sphere of space 67 kilometres across at our scale. And the sphere is, with the exception of a few grains and dust motes and the occasional icy body, empty. 67 kilometres of emptiness scattered with a few small things. That is the Sun's domain. That is everything our species has ever explored, everything we have ever visited, everything our probes and telescopes have ever directly encountered. All of it inside a sphere the size of a medium-sized country region at grain of sand scale. And beyond that, beyond the Oort cloud, beyond the edge of the Sun's gravitational pull, is interstellar space. And interstellar space is where the model really starts to show you what the universe is like. Part 4. The nearest star, 7 kilometres away. The nearest star to the Sun is called Proxima Centauri. It is about 4.24 light-years from us. At grain of sand scale, that distance compresses to roughly 280 kilometres. 280 kilometres. That is not the kilometre of walking. That is the kilometre of long-distance driving. If the grain of sand sun is on your kitchen table in one city, Proxima Centauri is a grain of sand on the kitchen table of a person who lives in a completely different city, perhaps in a different region of your country, hundreds of kilometres away. Let me say that differently. The nearest other star in the grain of sand model of the universe is not down the street. It is not in the next town. It is not even in the next county. It is across a region that would take hours to drive at highway speeds to cross. 280 kilometres. That is how far the nearest other star is at our chosen scale, and everything in between, all 280 kilometres of it, is almost perfectly empty. There are no stars in between the Sun and Proxima Centauri. There are no planets. There are no objects of any substantial size. There is only the diffuse interstellar medium, the very thin mist of hydrogen atoms and dust grains that fills the volume between stars. At grain of sand scale, that mist is so attenuated that you could set a laser beam going from the grain of sand Sun toward the grain of sand Proxima Centauri, and the beam would reach its destination without encountering any grain large enough to matter along the way. 280 kilometres of empty road, and at the far end, another grain of sand. That is the shape of the interstellar distance to our nearest neighbour. That is the shape of what astronomers mean when they say that the nearest star is far away. At every scale we care about, the distance is large. At real scale, 4 light-years, an unimaginable number. At grain of sand scale, 280 kilometres, a distance that dwarfs the length of any city. And Proxima Centauri is, by galactic standards, practically next door. The average distance between stars in the general neighbourhood of the Sun is closer to 5 light-years, which works out in our model to about 330 kilometres. If you mapped out the positions of all the stars within, say, 50 light-years of the Sun onto a three-dimensional grid at grain-of-sand scale, you would have a sprawling region of nearly empty space, punctuated at intervals of 300 kilometers or so by single grains of sand. Each grain, a star. Each interval between grains, a distance you would drive, not walk. Each grain alone in its own vast, quiet region, separated from every other grain by more space than most countries contain. This is the local stellar neighborhood at grain-of-sand scale. This is the region that contains the closest stars to our Sun. This is, in real terms, a sphere of space only about 100 light-years across. But at grain-of-sand scale it becomes a region measuring about 7,000 kilometers across, the width of a continent. Imagine every grain of sand in a continent-sized region of space, and then imagine that there are only a few hundred grains total in the entire region, spaced hundreds of kilometers apart from each other. That is the neighborhood. That is how empty it is. Part 5. The distance to the galactic center. Zoom out further. The Sun is not in the center of the galaxy. The Sun is out in a spiral arm, about 26,000 light-years from the galactic center. In real terms, that is a vast distance. In our grain-of-sand model, it becomes about 1.8 million kilometers. 1.8 million kilometers. Let me translate that into something you can picture. The Moon is about 380,000 kilometers from Earth. The average distance from the Earth to the Moon, 1.8 million kilometers, is more than 4 times the Earth-Moon distance, 4 lunar distances. From the grain of sand, Sun, on your kitchen table, the center of the galaxy, in our scale model, is more than 4 times further away than the real Moon is from the real Earth. And to get there, at grain-of-sand scale, you would have to cross about 5,000 intervening star grains, spaced at their characteristic distances, through the bright interior of the galactic disk. 5,000 grains of sand spread across a corridor 1.8 million kilometers long. And the corridor, even at grain-of-sand scale, is mostly empty. Between the grains, vacuum. Between the stars, interstellar medium. Between everything of substantial mass, the thin mist that fills the galaxy and provides almost no resistance to anything passing through. 5,000 grains of sand, 1.8 million kilometers. That is the radial distance from the Sun to the center of the galaxy, compressed down to the grain-of-sand scale. And at the center, if you could reach it in our model, you would find a supermassive black hole. The black hole itself is, at grain-of-sand scale, an object about 10 centimeters across, a fist-sized object, at the center of the galaxy, holding a mass 4 million times the mass of the Sun. A small, dense thing at the end of a corridor 1.8 million kilometers long, around which hundreds of billions of grains of sand orbit at their various distances. That is the shape of the galactic interior. That is what the Milky Way contains at its heart, at our scale. A fist at the center, orbited by grains of sand at intervals of hundreds of kilometers, across a disk that extends 1.8 million kilometers outward to the rim. Part 6. The Milky Way at grain-of-sand scale. The Milky Way galaxy, from one edge of its disk to the other, is about 100,000 light-years across, at grain-of-sand scale that compresses to roughly 7 million kilometers. 7 million kilometers. That is a distance I'm not sure I can render into a meaningful comparison with earthbound experience, because it exceeds every distance a human being encounters directly. 7 million kilometers is about 20 times the Earth-Moon distance, It is more than 7% of the real Earth-Sun distance. It is the kind of distance that, even at the compressed grain of sand scale, cannot be walked or driven or crossed in any human meaningful way. But the point of the model is not that it makes galactic distances walkable. The point of the model is that it provides honest ratios. And the ratio the model is telling us, when it says that the Milky Way is 7 million kilometres across at grain of sand scale, is that the galaxy is unimaginably larger than the distances between its stars. Think about this. In the model, the distance between the Sun and the nearest star is 280 kilometres. The distance across the whole galaxy is 7 million kilometres. The ratio between those two distances is about 25,000, which means that if you take the grain of sand Sun and imagine all the other stars in the galaxy as grains of sand at their proportional positions, the galaxy as a whole is 25,000 times wider than the gap between the two nearest grains. The galaxy contains about 100 billion grains. Those 100 billion grains are distributed across a volume so vast that even compressed to grain of sand scale, it is larger than anything humans have ever travelled. 100 billion grains of sand, spread across 7 million kilometres of space. That is, in honest ratios, what the Milky Way galaxy is. A vast, almost empty volume of space with a scattering of tiny bright objects embedded at great distances from each other, held together by the gravitational pull of a dark halo that extends 3 times further out than the visible galaxy. If you wanted to collect all 100 billion grains of sand from all over the galaxy and bring them to a single point, they would fill, at this scale, maybe a cupful of grains. That is the total content of stars in the Milky Way, measured by their compressed sizes. A cupful of grains scattered across a volume of space 7 million kilometres across. That is the ratio of stellar matter to galactic volume. That is how empty the galaxy is. Part 7. The local group and the nearest neighbour galaxies. The Milky Way is not alone. It is part of a small cluster of galaxies called the local group, which contains about 50 known galaxies of various sizes. The two largest members of the local group are the Milky Way itself and the Andromeda galaxy, which is somewhat larger. Andromeda is about 2.5 million light-years from the Milky Way. At grain of sand scale, 2.5 million light-years compresses to about 170 million kilometres. 170 million kilometres. That is, to put it in Earth terms, more than the distance from Earth to the Sun at its farthest approach in orbit. From our grain of sand Sun, the centre of the Andromeda galaxy is, in scale, about 1.1 times the real Earth-Sun distance away. And between the Milky Way and Andromeda, in our scale model, is a vast volume of space with almost nothing in it, some small satellite galaxies, some intergalactic gas, very thin, a few other large structures at varying distances, but mostly emptiness. Emptiness measured in tens of millions of kilometres, at grain of sand scale. Emptiness that dwarfs, by orders of magnitude, the distances between stars inside either galaxy. The two largest galaxies in the local group, which are, in cosmic terms, our closest neighbours, are separated by a gulf of empty space that, even at grain of sand scale, reaches across a distance larger than the real Earth-Sun gap. That is how far apart galaxies are. That is how sparse the large-scale structure of the universe is. And the local group, the cluster of galaxies we belong to, is itself a small feature in a much larger structure. Beyond the local group, in every direction are other galaxy groups, other clusters, other superclusters. The Virgo cluster, about 54 million light-years away, holds more than 1,000 member galaxies. The Coma cluster, 300 million light-years away, holds thousands more. The Laniakea supercluster, which includes the local group and many neighboring clusters, extends for more than 500 million light-years in its largest dimension. These structures, at grain-of-sand scale, become distances that are no longer meaningful to compare to anything in Earth experience. They are the large scale of the universe at which even the compressed scale model gives up. Part 8. The observable universe at grain-of-sand scale. The observable universe is a sphere of space about 93 billion light-years in diameter. That number, the 93 billion, may surprise you, because the universe is only 13.8 billion years old and nothing travels faster than light, but the universe has been expanding the whole time. Distances that were close together in the early universe have been stretched apart by cosmic expansion, so that the actual distance today at rest to the regions that are currently emitting the cosmic microwave background is much larger than the number of years the light has been travelling, 93 billion light-years across. That is the honest diameter of the currently observable universe. At grain-of-sand scale, 93 billion light-years becomes about 6.3 trillion kilometres. 6.3 trillion kilometres. That is the scaled diameter of the observable universe. That is, roughly, the distance from the Sun to the nearest star in real terms, before the compression. Or, to put it another way, the observable universe at grain-of-sand scale is about 2/3 of a real light-year across. The ratios have compressed the universe down, but even the compression is not enough to make the universe small by Earth standards. The universe is still staggeringly large. The grain-of-sand model only pretends to contain it. In practice, the model starts to fail around the scale of galaxy clusters. Beyond that, the ratios stay honest, but the resulting distances become so large that they exceed any distance you could imagine on or near Earth. And inside that 6.3 trillion kilometre sphere, at grain-of-sand scale, are roughly 2 trillion galaxies. 2 trillion. A number we recently had to correct upward by a factor of 10, based on new data from the James Webb Space Telescope. 2 trillion galaxies, each one a cupful of star grains scattered across a volume measured in trillions of kilometres, even at the compressed scale. Each galaxy, 7 million kilometres across in the model. The galaxies themselves separated from each other by intergalactic distances that, at grain-of-sand scale, dwarf all of the distances we have already walked through. The observable universe at grain-of-sand scale is a room that is too large to draw. A volume that is too large to travel through at any speed a human or even a spacecraft could achieve. A distribution of cupfuls of grains scattered across trillions of kilometres of mostly empty space, separated from each other by voids and filaments and intergalactic gulfs measuring dozens or hundreds of millions of kilometres at our compressed scale. And at the outermost edge, where the cosmic microwave background still glows faintly from the earliest moments we can still detect, is the boundary of what we can see. Not the boundary of the universe itself. The universe extends beyond the observable volume. How far beyond, we do not know. The observable universe is simply the part that has had time to reach us, the part whose light has had the billions of years needed to travel across the expanding space that separates us from it. 93 billion light-years, 6.3 trillion kilometres at grain-of-sand scale. 2 trillion galaxies. This is the universe. compressed as far as a coherent model can compress it, and still outrunning our ability to render it into any Earth-scale metaphor. The universe, even at grain-of-sand scale, is simply too large for the imagination. The model works for the local neighborhood, the planetary distances, the nearby stars. At galactic scale, the model starts to struggle. At cluster scale, it begins to fail. At the scale of the observable universe, the model shows us only that the universe is unimaginably large, which we already suspected, but now with slightly more precise numbers attached. Part 9. What a human being feels in a universe like this. Pause for a moment. Put down the grain of sand you have been holding. Let the model settle into your mind. And ask yourself, what does it feel like to live inside a universe where these are the honest ratios? The first thing it feels like for most people is small. The universe is so vast that any individual human, any individual species, any individual planet, any individual galaxy occupies a negligibly tiny fraction of the total. Our Earth is a dust mote orbiting a grain of sand that is one of 100 billion grains, making up a spiral galaxy that is one of 2 trillion galaxies in the observable universe. The ratios of our existence set against the scale of the cosmos are arithmetic that does not flatter us. We are small. We are embedded in something vast. But the second thing the model offers, if you sit with it long enough, is something different from the smallness. The model offers company, not loneliness, because the same ratios that make us small also make it possible in the arithmetic of probability that we are not alone. 2 trillion galaxies, each with 100 billion stars, each of those with some fraction of planets, some of those with the chemistry for life. The numbers produce, in any honest accounting, a universe in which biological chemistry is likely to have arisen in many places, not just this one. The universe is vast enough to hold countless forms of life, countless planetary histories, countless evolutionary paths. The emptiness that separates us from all of those other lives is vast. But the existence of the other lives somewhere in that emptiness is not mathematically unlikely. It is mathematically expected. And the third thing the model offers, if you keep sitting with it, is a kind of peace. The universe is large. The universe does not know we are here. The universe is indifferent to our existence. But in the very indifference of the universe, there is a kind of freedom. The stars do not judge. The galaxies do not care. The cosmic microwave background arriving from distances that exceed all imagination is not a message to us. It is simply photons that have been traveling for 13.8 billion years and happen to pass through our instruments on their way to wherever photons eventually end. The universe is not aimed at us. The universe is just there. And we, embedded inside it, are free to make of our small local existence whatever we want. The cosmic scale does not require anything from us. The cosmic scale simply provides the setting in which our much smaller lives unfold. This is perhaps the ultimate consolation of the scale model. Not that the universe is reassuring, because it is not. Not that the universe is warm, because it is not. The universe is cold, vast, mostly empty, indifferent, and ancient beyond any scale we can feel. But within the universe, in the small neighborhoods we actually inhabit, there is room for meaning. There is room for company. There is room for the long, slow human work of figuring out what to do with our fleeting time on our dust mote orbiting our grain of sand. And the model, by making the ratios honest, does not diminish that work. The model puts the work in context, a context that is larger than we are used to holding, a context that, once held, does not go away. Part 10. A final walk through the model. Let us take one last walk. Start with the grain of sand on the kitchen table. The sun. Hold it between your finger and thumb. Feel its small, solid, physical reality. That is our star, compressed. That is the center of everything you know. Step outward. The Earth, a dust mote, orbits the grain at the distance of a football field. The Moon, a smaller dust mote, orbits the Earth at about 1/2 meter from it. Mars, another dust mote, orbits at 160 meters. Jupiter, a pebble, at 550. Saturn, at 1 kilometer. Uranus, at 2 kilometers. Neptune, at 3 kilometers. These are the planets of our solar system laid out at scale. From your kitchen table outward, into your neighborhood, out across the houses and streets, out to the far edge of the neighborhood where Neptune sits in somebody else's yard. Step further. Out into the farmland, out to the edge of your town, out to the next town over. Voyager 1 at 26 kilometers from the grain of sand sun, coasting slowly outward, still not at the edge of the sun's gravitational domain. Keep going, past the Oort cloud at 67 kilometers from the grain, beyond the sun's last icy objects, into interstellar space. Step further. 280 kilometers from the grain of sand sun, across a region that would take hours to drive at highway speeds, is another grain of sand on another kitchen table. Proxima Centauri, the nearest star. And between the two grains, nothing of substantial mass. Empty road, empty country, empty air. 280 kilometers of mostly perfect emptiness, broken only by the thin mist of the interstellar medium, which at grain of sand scale is too thin to even register as something present. Step further. Across the disk of the galaxy, past 5,000 intervening grains of sand, each one a star in its own right, each one hundreds of kilometers from its neighbor. 1.8 million kilometers from your kitchen table, the center of the galaxy. A fist-sized, dense object orbited by hundreds of billions of grains at the heart of the Milky Way. Step further, 7 million kilometers across, the edge of the galactic disk. Beyond that, intergalactic space. Dark, mostly empty, populated by occasional small satellite galaxies and the very thin mist of intergalactic gas. Step further, 170 million kilometers away, the Andromeda Galaxy, another cupful of grains, another 7 million kilometers across, our nearest large neighbor. Between the two, a gulf that, even at grain of sand scale, exceeds the real distance from Earth to the Sun. Step further still, out across the local group, out to other galaxy clusters, out across Laniakea, out into the far regions of the observable universe. 6.3 trillion kilometers at our compressed scale, holding 2 trillion galaxies, scattered across voids and filaments, connected by the ancient light of the cosmic microwave background. And at the outermost edge, the boundary of what we can see. Not the edge of the universe, the edge of the observable part. Beyond that, more universe, stretching out to unknown distances, possibly infinite, containing possibly infinite more galaxies, possibly infinite more stars, possibly infinite more worlds. All of this, compressed down by a factor of 1.4 billion, still exceeds anything a human being can walk across, drive across, fly across, reach in any human lifetime. The compression is not enough. The universe is too large for the model to tame it. The model only reveals, through its own inadequacy at the largest scales, how vast the thing we live inside really is. Come back. Hold the grain of sand again. Let it sit between your finger and thumb. That is our star. That is the center of our world, and around it, at distances that the mind can barely hold, is the universe. A universe of 2 trillion galaxies. A universe of hundreds of sextillions of stars. A universe of sextillions of planets, many of which orbit in the habitable zones of their suns, many of which have had chemistry similar to ours. Many of which may hold, at this very moment, forms of life or structure that we have not yet detected and may not detect in any foreseeable future. We are one of the places, one dust mote around one grain of sand in one cupful of grains, in one region of one cluster, in one corner of one observable volume of one universe. And our ratios compared to the cosmos are vanishing. We are small, unimaginably small, but we are here. We are looking. We are at this moment holding the whole ratio in our minds, asking ourselves what it means. That is not nothing. That is perhaps a lot. Part 11. The speed of light at grain of sand scale. Here is something the scale model does that other scale models usually skip. It has implications for time as well as for distance. We compressed the sun down by a factor of 1.4 billion. That compressed every distance in the universe by the same factor. But what does it do to the speed of light? Light, in the real universe, travels at about 300,000 kilometers per second. In our grain of sand model, if we shrink distances by a factor of 1.4 billion but leave time alone, we have to also shrink the speed of light by the same factor. Divide 300,000 by 1.4 billion and you get about 0.2 millimeters per second, 0.2 of a millimeter per second. Light at grain of sand scale moves at about 0.2 of a millimeter per second. That is slower than the second hand on a wristwatch. That is slower than almost anything you will watch in ordinary life. That is essentially a creep, a visible glacial motion, a small amount of forward progress that your eye can track and wait for. And with light moving at 0.2 of a millimeter per second in our model, consider what interstellar distances become in temporal terms. Light from the grain of sand sun would take, at that compressed speed, a little more than 4 years to reach the grain of sand, Proxima Centauri, 280 kilometers away. That is honest. Light in the real universe takes 4.24 years to cross that distance. In our model, which has compressed distance but not time, the 4-year travel time is preserved. Which means that if you could somehow sit at the grain of sand sun and watch a beam of light crawl outward at 0.2 of a millimeter per second toward the grain of sand, Proxima Centauri, 280 kilometers away, you would be watching for more than 4 years. 4 years of continuous observation, 4 years of unbroken patience, and the light would still not have arrived. Let me say that again so it registers. At grain of sand scale, where the sun is a grain you can hold in your finger, and the nearest star is a grain 280 kilometers away, light itself moves so slowly in the compressed frame that crossing the gap between the two grains takes 4 years. 4 years of continuous unbroken forward motion at 0.2 of a millimeter per second. That is the temporal shape of an interstellar journey preserved through the scale compression. The compression shrinks the distance. The compression does not shrink the time. And so the time becomes, visually, enormous. A glacial creep. A travel that you can watch but cannot hurry. This is maybe the single most important feature of the scale model. Because most popular treatments of cosmic distance treat space and time separately. They say, look, the distance to the nearest star is 4 light years, and they move on. The phrase 4 light-years to most people is just a number. It does not communicate the temporal weight of what a 4 light-year journey actually is. But in the scale model, where distance is compressed and time is not, the weight becomes visible. The light itself, slowed down to match its real temporal rhythm, crawls across the gap at a speed you can measure with a ruler and a stopwatch, and the crawling takes years. And this is just for the nearest star. For a trip to the galactic center at 1.8 million kilometers in the model, light would take 26,000 years of compressed model time. 26,000 years, longer than the entire span of recorded human history. That is how long a photon would crawl across the interior of the galaxy in our model before reaching the center. 26,000 years of uninterrupted motion at 0.2 of a millimeter per second. And this is honest. Light really does take 26,000 years in the real universe to cross the corresponding real distance. The scale model thus contains, at its most profound, a reminder that has nothing to do with size and everything to do with time. The universe is old. The universe is slow. The universe is structured so that the things in it are separated not just by distance, but by the time it takes any signal to travel between them. And that time, preserved honestly in the model, forces us to face something that abstract numbers let us avoid. The universe is not just large. The universe is also old and temporally vast. Every point in the universe is separated from every other point by intervals of time that dwarf human lifetimes. Every connection across the cosmos is a connection across not just a distance, but a duration. And the duration is the thing that makes the connection hard. Part 12. Travel at human scale speeds. In the model, if light itself crawls across the model at 0.2 of a millimeter per second, what about real spacecraft? Real spacecraft that we have actually built. How fast would they move in the model? Voyager 1 moves through real space at about 17 kilometers per second. In the compressed model, that speed becomes 1.4 billion times smaller, which works out to about 12 nanometers per second. 12 nanometers per second, that is slower than bacteria moving across a microscope slide. That is slower than the growth rate of a fingernail. That is so slow that on human observation timescales, Voyager at model speed would appear not to be moving at all. A grain of dust, creeping along at nanometer per second speeds. You could watch it for hours and see no change. And yet this is the fastest outbound spacecraft humanity has ever built. This is the best we have done in nearly 50 years of space exploration. At 12 nanometers per second in the model, how long would Voyager take to reach Proxima Centauri, which sits 280 kilometers away? The arithmetic is brutal. 280 kilometers divided by 12 nanometers per second gives a time of about 70,000 years. 70,000 years. In the real universe, Voyager will never reach Proxima Centauri. Voyager is not headed in that direction, and even if it were, the spacecraft would take tens of thousands of years to get there. In the scale model, we can feel this in a way that the raw number cannot convey. A grain of dust, creeping along at 12 nanometers per second, crawls across 280 kilometers in 70,000 years of continuous motion. No stopping, no refueling, no course corrections, just the slow, silent crawl of nanometer progress, carried across highway-length distances over spans of time that exceed civilisations. This is what it means to be a species that has only just started to leave its home system. This is what it feels like, at honest ratios, to live inside a universe where the nearest other star is this far away. Our best technology, our fastest spacecraft, scaled down to the grain of sand model, becomes a speck of dust moving at nanometer speeds, and the distance it needs to cross to reach the very nearest neighbour takes 70,000 years to traverse. Let that land for a second. 70,000 years. That is longer than any human civilization has lasted. That is longer than writing has existed. That is longer than the agricultural revolution. 70,000 years of continuous flight at the fastest speed we have ever built to reach the nearest grain of sand to our own. In a model where that grain sits on a kitchen table only 280 kilometres away from us, the distance is, at scale, local. The time is, at honest ratios, cosmic. This is the tension the model exposes. Distance can be compressed. Time cannot. The ratio between them, the thing we call the speed of light, is a fixed property of the universe, and no scaling can escape it. Every honest model of the cosmos carries this tension inside it. The universe is large in space, and the universe is correspondingly long in time. Any journey across space requires a matching expenditure of time. And the expenditure is brutal. The expenditure exceeds every human category. The expenditure is the actual obstacle to interstellar travel, more than fuel, more than engineering, more than ambition. The expenditure is time, and we do not have enough of it. Part 13. What 1 second of light covers at grain of sand scale. Let us flip the model around. Instead of asking how slowly light moves when we compress distances, ask how much ground light covers, in our compressed model, in a single second. In the real universe, light travels 300,000 kilometres in 1 second. That is long enough to reach the moon from Earth, and then some. In the scale model, that becomes 0.2 of a millimetre per second. In 1 second, light covers 0.2 of a millimetre of model space. 0.2 of a millimetre in 1 second. Pick up a ruler. Look at the smallest gradation, the 1 millimetre mark. Light, in our model, in 1 second covers about 1/5 of that smallest gradation. Now, think about what a second of light is. In the real universe, it is a substantial distance. The Earth and the Moon are about 1.3 light seconds apart. You can, on a small enough model, render a light second as a real distance, but in our grain of sand model, a light second is 1/5 of a millimetre, almost invisible, a tiny crawl that you could barely see without magnification. This, again, is the temporal weight of the cosmos made visible through the model. The thing we casually call the speed of light, the fastest speed anything in the universe can move, becomes, when compressed by the same factor that compresses distances, a creep so slow that ordinary human observation cannot see it progressing. And yet it is, in the honest ratios of the real universe, the absolute fastest anything can travel. Nothing is faster. No signal, no object, no information. Now, imagine a message. Someone at the grain of sand sun sends a radio signal toward the grain of sand Proxima Centauri at the full speed of light. In the model, the signal crawls outward at 0.2 of a millimetre per second. The grain of sand sun is in your kitchen. The grain of sand Proxima Centauri is in another city, 280 kilometres away. The signal leaves your kitchen and creeps across the air at 1/5 of a millimetre per second. It takes more than 4 years to cross the 280-kilometre gap. 4 years of continuous outward motion. 4 years for the message to arrive. And if the recipient replies instantly, 4 more years for the reply to come back. A simple hello hello exchange between our grain and the nearest grain takes, at model scale honest time, more than 8 years to complete. 8 years for a single round trip of the fastest possible signal between the two closest grains of sand in the model. Any conversation with anyone anywhere else in the universe is going to be like this: long, patient, asynchronous. There is no way to cheat the speed of light. There is no way to make communication faster. And when the distances are as large as interstellar or intergalactic distances, the communication time becomes, in practice, a barrier. Not because the signal gets lost, because the reply takes so long to arrive that entire generations can pass before a single exchange is completed. The model makes this visible. The model takes the abstract speed of light number and turns it into a physical crawl that your eye can watch, and then layers onto that crawl the honest temporal cost of crossing real distances. And what emerges from that combination is the reason we have not heard from anyone else. The emptiness is hard to cross with signals. The signals themselves are slower than most people's intuitions admit. The round-trip time between neighbouring grains in the model already exceeds human patience. For more distant grains, for grains on other continents in the compressed cosmic room, the round trip becomes unbearable. Civilisations rise and fall on timescales that barely permit the first signal to propagate to the next grain, let alone receive a reply. Part 14. The model shows us why we are alone. Let us bring together everything the model has shown us. The sun is a grain of sand. The nearest other star is a grain of sand 280 kilometres away. Light itself crawls through the model at 0.2 of a millimetre per second. The fastest spacecraft we have ever built would take 70,000 years of the model's time to cross from one grain to the other. The galaxy contains 100 billion grains scattered across 7 million kilometres of compressed space. The observable universe contains 2 trillion of these galaxies at distances of tens or hundreds of millions of kilometres from each other in the model. What does this mean for the question of cosmic company? It means that if there are other intelligent civilizations in the universe, they are almost certainly separated from us by distances that make communication extraordinarily hard. Even if there were a civilization at every one of 100 billion grains in our galaxy, broadcasting constantly at the power of our most powerful radar transmitters, most of those signals would be too faint by the time they reached us to be detected by our current instruments. The inverse square law of radiation means that a signal weakens as it spreads out, dropping off as the square of the distance. A signal strong enough to be received at 280 kilometres in the model, meaning from the nearest neighbouring grain, would be 1,000 times weaker at the distance to a grain a few grains further out, and 1 trillion times weaker at the distance to a grain on the other side of the galaxy. The galaxy, in other words, is not just large in a spatial sense, it is acoustically large, it is communicatively large. Signals fade across it. Voices vanish into the intervening distance. And by the time a signal reaches a grain on the far side of the galaxy, the signal has become so diffuse that only the most extraordinarily sensitive receiver could hear it, and only if it is aimed in exactly the right direction at exactly the right moment. This is what the scale model shows when you hold it carefully and think through the implications. The emptiness between grains is not just empty space. It is also an acoustic barrier, a diffusion of any signal that tries to cross it. A reason why the sky, when we listen to it with radio telescopes, is mostly silent even if the sky is full of civilizations. The silence is not a proof of absence. The silence is a consequence of the geometry. The distances are enormous. The signals fade with distance. And so the galaxy, even if populated, sounds mostly empty to our ears because our ears are tuned to a receiver that cannot hear signals beyond a certain distance. The same logic applies at the intergalactic scale. If there were civilizations in every one of 2 trillion galaxies, the signals from the nearest other galaxy would still be diluted by the hundreds of millions of kilometers between us and them in the model, which translates to the millions of real light years of real intergalactic space. Any message sent from Andromeda toward the Milky Way would need to be broadcast at power levels far exceeding anything we have ever produced for it to arrive here still detectable. And even then, it would take 2.5 million years to arrive. Every signal from every other galaxy is delayed by geologically significant spans of time. The universe, acoustically, is not just wide, it is old. And the ages of signals arriving here are, by the time they reach us, older than the species they describe. This is the answer to the Fermi Paradox that the scale model provides. Not an answer that says we are alone. An answer that says we are separated. By distances, by time, by signal attenuation, by the geometry of a universe in which every voice fades before it can cross the gap to the next listener. And so, even if the universe is full of voices, we hear only silence, because the voices do not carry, because the space is too large, because the time is too long, because the medium is too empty. The model, in the end, offers a gentler explanation than cosmic loneliness. The model offers cosmic isolation, not absence. The universe may be populated, the universe may be full of life, and we may still, realistically, never hear from any of it. Not because no one is out there, because the structure of the cosmos makes hearing across the gulf an almost impossible task. And we have only been listening for a century, and we have only been signaling for a few decades. And the signals we have sent out have travelled, in the model, only a few millimetres from our grain. They have not yet reached the nearest neighbouring grain. They will take another 70,000 years at current technology to get even that far. We are not alone because nothing is there. We are alone because nothing has had time or power or proximity to reach us. Those are different kinds of alone. The universe permits the second kind while remaining fully consistent with the first kind being wrong. That is maybe the most honest consolation the model can offer. You are not necessarily alone, you are just isolated, and isolation at honest ratios is the default condition of everything in the cosmos. Part 15. Why the model matters. Scale models of the universe are, in one sense, just educational tools. They are demonstrations, they help children understand, at a rough level, how the solar system is laid out. They appear in planetariums, in science museums, in textbook diagrams. They are not, by themselves, scientific contributions. No researcher does original astronomy by playing with a grain of sand on a table. But in another sense, scale models are one of the most important cognitive tools we have for grasping the cosmos, because the cosmos, at its real dimensions, is not something the human mind can directly hold. The numbers are too large, the distances are too vast, the relationships between the different scales, planetary, interstellar, galactic, intergalactic, are too different in magnitude to be carried in one mental image without compression. The scale model compresses. The scale model takes the raw numbers and converts them into bodily scale distances, distances you can walk, drive, or point at. And in the act of compression, the scale model reveals ratios that the raw numbers hide. When you learn that the Sun is 150 million kilometers from Earth, that number lives in one part of your brain. When you learn that Proxima Centauri is 40 trillion kilometers away, that number lives in a different part. The ratio between the two, the fact that interstellar distances are hundreds of thousands of times larger than Earth-Sun distances, is a ratio your brain has to actively compute to hold. The numbers by themselves do not enforce the ratio. They just sit there, each large, each detached from the other. The scale model enforces the ratio. When you place the grain of sand Sun on the table and the dust mote Earth a football field away, and then you have to imagine the nearest other grain being 280 kilometers away, the ratios become visible. You can feel them. Your body knows the difference between a football field and 280 kilometers, the difference between a local walk and a cross-country drive, the difference between what you can reach with a short trip and what requires a journey. And when you apply those body-level intuitions to the universe, you come away understanding something that the raw numbers alone could not give you. This is why the model matters. Not because the model is the science. The model is not the science. The science is in the real numbers, in the calibrated measurements, in the peer-reviewed papers. The model is a tool for helping ordinary people and ordinary scientists in moments of contemplation feel what the numbers mean. And feeling what the numbers mean is, often, the beginning of the kind of honest engagement with the cosmos that makes understanding possible. A grain of sand, 280 kilometers to the next grain, 7 million kilometers across the galaxy, 170 million kilometers to the next galaxy, trillions of kilometers to the edge of the observable universe, light moving at 1/5 of a millimeter per second. Our fastest spacecraft at 12 nanometers per second, every signal fading with distance, every journey taking cosmic spans of time, every intergalactic gulf holding its silence like a held breath. The model shows you all of it. The model makes honest ratios visible. The model does not answer the deep questions about what the universe is, or why it is the way it is, or whether we are alone in it. The model only shows you where you are, a grain of sand at the center of a room, with the rest of the universe at honest scale, spread out around you. And you, on your small dust mote, orbiting your grain, looking up at a sky whose honest dimensions you can now hold, however briefly, in the palm of your hand. That is the gift of the model, not a final understanding, a provisional one, a way of seeing where you live, a way of feeling the shape of the universe for the time it takes to hold a grain of sand between your finger and thumb and let the ratios settle around you. Hold the grain. Let the universe settle around it. Let the scale be honest. Part 16. A walking tour, one step at a time. Let us try something concrete. Let us do the model with our feet. You will not actually do this, probably, but you can imagine it, and the imagination is the whole point of the model. Stand in the middle of a large, empty room. Put the grain of sand on a small table in the center. That is the sun, your starting point. Now take one step away from the table, one regular human step, about 3/4 of a meter. You are now at the scale of the model, past the orbit of Mercury. If you look back at the grain of sand, you cannot see it from this distance. It is too small. Your starting point has disappeared from view, and you have only walked a single step. Take another step. You are past Venus, another, you are past Earth. The dust mote that represents Earth is somewhere near your foot, orbiting the grain you cannot see, at a radius of about 1.5 meters from the grain. Another step. past Mars, another step or two, and then a long, slow walk, dozens of steps, before you reach Jupiter's orbit at about 550 meters. The length of several football fields, you have crossed most of the living room and are out the door and down the hall and out of the building. Keep walking. Saturn's orbit, a full kilometre from the grain. You are a 10-minute walk from the table in the middle of the empty room. Uranus, 2 kilometres. A half-hour walk. Neptune, 3 kilometres. 40 minutes of walking. And the Oort cloud, the outer edge of the Sun's gravitational domain at 67 kilometres. That is a drive, not a walk. That is out of the city, into the countryside, across the suburbs, through the farmland. 67 kilometres. The boundary of the Sun's influence at this modest grain of sand scale requires leaving the urban area entirely. And we have still not reached the nearest star. Keep going. 280 kilometres from the starting table. That is the distance to Proxima Centauri in our model. That is further than most people drive in a day. That is more than 3 hours of highway driving, non-stop, at 100 kilometres per hour. 3 hours. Across towns, past cities, through multiple regions of your country. And at the end of that drive, after leaving the original grain of sand behind and travelling across 300 kilometres of road, you arrive at another grain of sand, the nearest star, sitting on another table in another town. This is the thing the model makes walkable in a way that raw numbers never quite do. You can feel the distance from one grain to the next. Your body knows what 300 kilometres feels like because you have travelled that far at some point in your life, probably many times. And when your body applies that feel to the distance between our sun and the nearest other star, you understand viscerally what interstellar space is. It is a long drive between every star and every other star. A long drive that no spacecraft has ever attempted. A long drive that our fastest ships would take 70,000 years to make. A long drive that light itself crosses in more than 4 years of continuous travel. The model, by rendering the drive in terms your body can understand, makes the interstellar scale feel real. And once it feels real, you will never again be able to hear the phrase 4 light years without feeling, in the background of the phrase, the weight of 300 kilometres on a highway, the weight of a drive that takes half a day and has almost nothing in it. Part 17, the habitable zone at our scale. Let us zoom back in for a moment to the grain of sand and look at something specific. Around every star there is a region of space where the temperature is right for liquid water to exist on the surface of a rocky planet. Not too hot, which would boil the water away. Not too cold, which would freeze it. A narrow range, usually called the habitable zone or sometimes the Goldilocks zone, where life, as we know it, has a chance. The habitable zone around the Sun extends from about 0.9 times the Earth-Sun distance out to about 1.5 times the Earth-Sun distance. That is a fairly narrow range. In our grain of sand model, with the Earth-Sun distance at 107 meters, the habitable zone becomes a ring extending from about 96 meters out to about 160 meters from the grain. A band of space about 60 meters wide. A band less than the length of a single football field. That is where life as we understand it can exist. A narrow ring around the Sun, about half a football field in width, within which liquid water can persist on the surface of a rocky world for long enough to allow biology to develop. And inside that ring in our real solar system, only Earth qualifies. Venus is too close to the Sun, and its runaway greenhouse effect has boiled away any liquid water it once had. Mars is at the outer edge of the zone and has lost most of its atmosphere, so any liquid water is now underground. Earth, the middle planet, has the right mass, the right distance, the right atmosphere, the right magnetic field, the right history. Earth is the only place in the solar system where life, as we know it, has demonstrably existed. One planet in one habitable zone around one star. That is the concrete case we have in front of us. Everything we know about life in the universe, every sample, every example, comes from this one dust mote orbiting this one grain of sand, and scaling this observation outward to other stars with their own habitable zones, each about half a football field wide in our grain of sand model. The question becomes how often the dust mote at the right distance develops the right conditions. How often the narrow ring gets populated by an organism capable of asking about itself, we do not know. That is the honest answer. We have one data point, our own planet. And from one data point, no statistical generalization is possible. The habitable zone exists around every star. The habitable zone is a narrow ring. Whether a rocky planet forms inside that ring, whether that planet maintains the right conditions, whether biology emerges, whether it persists long enough to evolve into anything complicated, all of these are open questions with unclear answers. The Drake equation is the traditional way astronomers have framed this uncertainty. It lists the factors that would need to be multiplied together to estimate the number of detectable civilizations in the galaxy, the rate of star formation, the fraction of stars with planets, the fraction of planets in habitable zones, the fraction on which life develops, the fraction where intelligence arises, the fraction where technology emerges, the fraction that become detectable, and finally, the average lifetime of a technological civilization before it either collapses, transforms, or falls silent. At grain of sand scale, the Drake equation is a walk through a galaxy of 100 billion grains, asking how many of them have the right setup around them to support a narrow habitable ring with a thriving occupant that happens to be broadcasting at this moment in cosmic time. The question is not whether there are many grains. There are 100 billion. The question is what fraction of those grains meet all the subsequent conditions. And the answer depends on parameters that we do not yet know how to measure. What we know is that the habitable zone exists around every star. What we do not know is how often the zone is occupied by something that notices. The scale model cannot answer this question. The scale model only makes the question vivid. Here is a galaxy of 100 billion grains, each one with its narrow ring, each one potentially populated or potentially barren. We do not know the fraction, we only know that we are one of the populated ones. Beyond that, we wait. Beyond that, we keep looking. The scale model holds the question. It does not solve it. Part 18. The cosmic microwave background at scale. At the very edge of our scale model, at the outermost boundary of what we can see, is a glow that permeates the entire sky. Not a bright glow, not visible to the naked eye. A glow in the microwave part of the electromagnetic spectrum, detectable by specialized instruments, coming from every direction in the sky with almost exactly the same intensity. This is the cosmic microwave background. It is the oldest light in the universe, emitted about 380,000 years after the Big Bang, stretched by cosmic expansion into microwaves during its 13.8 billion years of travel to reach our instruments. The cosmic microwave background is, in a real sense, the wall of the observable universe. It is the furthest thing we can see, because anything further is still inside the opaque plasma of the very early universe, before light could travel freely. The CMB is the boundary of our view. Beyond it we cannot see, not with the current physics. At that boundary the universe fades from observable to unobservable. At grain of sand scale, the cosmic microwave background forms a spherical shell surrounding our grain. The shell is about 6.3 trillion kilometres in diameter, which we mentioned earlier. The shell is, at the compressed scale, vast, but not infinite. It is a boundary. Beyond it, we cannot see. And the light arriving at us from the shell has been in transit at the real speed of light for 13.7 billion years. That is almost the entire age of the universe. At grain of sand scale, where light moves at 0.2 of a millimetre per second, the journey of a CMB photon from the shell to our instruments takes, by the same compression of distance and preservation of time, 13.7 billion years of model time. The same 13.7 billion years. The model does not compress this. The time is real. Every microwave photon hitting your radio antenna from the cosmic background has been travelling for 13.7 billion years. 13.7 billion years. Longer than the age of the Earth by a factor of 3. Longer than the age of the Sun by a factor of 3. Longer than the formation time of our galaxy by a factor of 2. The photons arriving from the CMB are older than essentially everything we know of, everything that has a history, everything that has changed during its own existence. Those photons have been in flight since before there were any galaxies to produce them. They are a snapshot, preserved in electromagnetic form, of the universe as it was when it was almost unimaginably young. This is what the cosmic microwave background represents, a signal carrying the earliest recoverable information about the universe, travelling continuously since before any of the structures we now see existed. When you point an antenna at the sky in any direction and pick up the microwave hiss of the background, you are listening to an echo from the birth of the cosmos. An echo that has been travelling for longer than almost anything in the universe has existed. An echo that reaches us at the compressed scale of our model from a distance of 6.3 trillion kilometres and has taken the full temporal weight of the universe's history to complete the journey. The model, even in its compressed form, cannot make this experience feel small. The cosmic microwave background is not a small feature. It is the edge of our observable cosmos. It carries the oldest information we can receive. It fills the sky in every direction with its patient photons, and the structure of the universe at its largest scales is written into the tiny temperature fluctuations of the CMB map. If you want to know the shape of the universe, you study the CMB. If you want to know its age, you study the CMB. If you want to know its composition, you study the CMB. Every major cosmological measurement of the last 3 decades has, in one way or another, come from the careful analysis of that ancient microwave signal. At grain of sand scale, the CMB is the outer surface of the room. Beyond that surface, the model does not extend. Beyond that surface, the universe continues, but we cannot yet see it. And whether we will ever be able to see it is an open question, one that depends on the future expansion of the universe and on the instruments we develop in the centuries to come. Part 19. The dark universe at sand scale. We have been talking about the visible universe, the part made of stars and galaxies and planets and gas, the part that emits or reflects photons we can detect. But the visible universe is only about 5% of the total mass-energy content of the cosmos. The other 95% is something else, something that does not produce light, something that, at our grain of sand scale, does not even have a physical rendering we can point at. 27% of the cosmic mass energy is dark matter. This is the stuff we talked about in the galactic context, an unknown form of matter, probably a new kind of particle not yet detected in any laboratory, whose gravitational effects we observe, but whose direct detection has so far eluded us. Dark matter outweighs ordinary matter by a factor of about 5 to 1. In our scale model, the visible galaxies are embedded in much larger halos of dark matter, which surround and outweigh them. The other 68% of the cosmos is something stranger still. It is called dark energy. And dark energy is not matter at all. Dark energy is, as far as anyone can tell, a property of empty space itself. A kind of pressure or tension that exists in every cubic centimetre of vacuum throughout the universe. As the universe expands, more volume of empty space is created, and because dark energy is a property of the vacuum, the total amount of dark energy in the universe increases with the expansion. Dark energy is driving the expansion to accelerate. It is the reason the universe is expanding faster now than it did in the past. It is the reason the future of the universe as currently modelled is one of ever-increasing emptiness, with galaxies receding from each other faster and faster, until eventually almost all of them are beyond the reach of any future observer. At grain of sand scale, how do you render dark energy? You cannot directly. Dark energy is not a thing with a location, it is a property of the space between things. Everywhere in our model, everywhere in the gaps between grains, there is dark energy present, very diffuse, very faint, but pervasive. The gaps are not empty. The gaps contain dark energy, and the dark energy is driving the gaps to grow. This changes the shape of the model in a subtle way. The scale model we have been walking through is a snapshot, a frozen moment. In the real universe, the distances between galaxies are slowly growing, and over billions of years, the growth becomes significant. In 1 trillion years, if current models are right, the galaxies outside our local group will have receded so far that their light will no longer be able to reach us. They will have crossed a kind of horizon beyond which communication becomes impossible. Future observers in that far future universe will see only a handful of local galaxies around them, with the rest of the cosmos gone into a receding darkness that no signal can ever recross. The emptiness we measured in this video, the trillions of kilometres of space at scale, the vast voids between superclusters, is not static emptiness. It is emptiness that is itself growing, growing because of dark energy, growing because of a property of the vacuum that we can measure but do not yet understand. This is the deepest level of the emptiness picture. The universe is mostly empty, and the emptiness is expanding. Every void becomes larger. Every intergalactic distance becomes longer. Every cosmic signal has to work harder to reach its destination as the destination moves further away during the signal's own flight time. The universe, in this sense, is a structure whose defining feature is becoming, with time, even more defining, more empty, more isolated, more separated into patches of matter that cannot easily communicate across the widening gulfs. At grain of sand scale, you cannot see this happening. The model is a snapshot. But if you could watch the model over the enormous spans of cosmic time, you would see the grains slowly drifting further apart, the intergalactic distances slowly stretching, the void slowly deepening, the overall density of the universe slowly decreasing as the same amount of matter occupies a larger and larger volume. That is the direction the universe is moving. That is where we are heading. And inside this slowly emptying cosmos, we sit on our grain, looking out, seeing what we can see while we can still see it, aware, at some level, that our window of observation is bounded by the expansion, aware that future generations looking out at their own universe will see less than we do, aware that billions of years from now the universe will be so empty that the few local grains still visible to any hypothetical observer will appear to sit alone in a vast, silent darkness with no evidence of any larger structure beyond. That is the future shape of the emptiness. That is where the model is heading, over spans of time that make human civilization look like a frozen instant. The universe is mostly nothing, and the nothing is growing. Every moment, a little more. Every generation of stars, a little more. Every cycle of cosmic time, a little more. Part 20. The deepest lesson of the model. After 20 odd parts of walking through the scale model, let us try to distill what the model is actually for. The model is not a map. The universe is not a room with grains of sand on a table. The model is a translation. It takes the raw numbers of astronomy, which are too large for the human imagination to hold directly, and renders them into body-scale distances that our intuitions can feel. The translation is not perfect. The model fails at the largest scales, where even the compressed distances exceed any earthbound experience. But for the local neighborhood, for the stars near us, for the journeys we might one day attempt, the model is useful. The model makes things feelable, and what the model reveals when you work through it carefully is a set of relationships that the textbooks do not always emphasize. The sun is small. The solar system is mostly empty. The nearest star is far away by any human standard, and light itself crawls across the gap at a pace that preserves the difficulty of the crossing. The galaxy contains a vast number of grains, scattered across a volume that dwarfs any single grain by orders of magnitude. The intergalactic medium is emptier still. The universe at its largest scales is a vast, mostly empty structure whose bright regions are minor exceptions to the general rule of darkness and quiet. This is what the model teaches. And the teaching is valuable not because it gives you new information, but because it gives you new intuitions. You already knew the numbers if you have been paying attention to any popular science writing in the last decade. What you did not have was a feel for the ratios. The feel is what the model provides. The feel is what turns astronomy from a recital of distances into a lived sense of cosmic position. And the cosmic position matters, because without it, the conversations we have about space and about life and about the possibility of other civilizations and about the future of our own existence tend to drift toward either dismissal or mysticism. Dismissal, because the numbers seem too large to take seriously, or mysticism, because the numbers seem to demand a significance they cannot deliver. The model grounds both drifts. The model reminds you that the universe is real, that the numbers are honest measurements of real distances, that the emptiness is a real feature of the real cosmos, and that our existence inside it, however small, is not thereby meaningless. It is just located. It is just situated. It is at this particular grain of sand, in this particular corner of the galaxy, at this particular moment of cosmic time. Situation is not insignificance. A small thing in a large place is still a thing, a single grain of sand, held between finger and thumb. is still real. The compression does not erase the grain. The compression only reveals what surrounds it, and what surrounds it at honest ratios is the universe. Hold the grain. Hold the universe around it. Hold both, for a moment, in your mind. That is what the model offers, not an answer. A way of holding the question, a way of holding at the same time the small and the large, the near and the far, the dense and the empty. The universe rendered as a room you can stand inside with the grain on the table in the center, and yourself, small and real and present, walking slowly outward through the layers of the compressed cosmos, measuring everything as you go. That is the gift of the model. It teaches the body to feel the cosmos. It turns numbers into distances, distances into walks, walks into understanding. And the understanding, though it never completes, is always a little better than it was before you started walking, a little more honest, a little more calibrated, a little more ready to look up at a real sky and see, in the pattern of the stars above you, the same structure that the model has been showing you on the table. The same grain, the same ratios, the same universe, the only universe there is, part 21, a second grain, and the silence between them. Let us end by focusing in on just two grains, ours and the nearest one, the Sun and Proxima Centauri. Two grains of sand sitting on two tables in two rooms in two different cities 280 kilometres apart at our scale. Nothing between them except the road that connects the two cities, empty of anything but air and the occasional passing car. Now imagine a person standing at our table, looking at our grain. That is us. Now imagine a person standing at the other table, looking at their grain. That is the hypothetical inhabitant of a planet orbiting Proxima Centauri. We do not know if such a person exists. As of the writing of this video, we have detected 2 planets in the Proxima Centauri system, and at least one of them is approximately Earth mass and sits inside the habitable zone of its star. Whether life has arisen on that planet, we do not know. Whether intelligent life has arisen, we do not know. Whether such life, if it exists, has any technology or interest or capacity for interstellar communication, we do not know. We simply know that there is a grain of sand in another city, at the distance of 280 kilometers from ours, with a rocky world the right distance away from it to potentially support life, and we are watching it. We are pointing our instruments at that grain. We are listening for signals. We are observing the transits of its planets. We are doing everything our current technology permits to learn whether anything is happening there, on that distant grain, around that distant rocky world. If the inhabitants of that world exist and are doing the same thing, pointing their instruments at our grain, listening for our signals, watching our planet's transits, then we are in some sense in parallel. 2 civilizations on 2 grains, each studying the other from its own side of the 280-kilometer gap, each unable to cross it, each unable to even exchange a simple signal within any reasonable human timescale. A signal sent from our grain takes more than 4 years to reach theirs. Their reply takes more than 4 years to come back. A simple hello-hello exchange takes 8.5 years minimum. No faster communication is possible. No cheat around the geometry exists. This is, at the most concrete level, what the grain of sand model reveals about our cosmic situation. We are not alone in the sense that the universe is too large for us to be the only dust mote with a thriving ecosystem. The numbers argue against it. but we are isolated, in the sense that our nearest potential neighbour is on another grain of sand hundreds of kilometres away at model scale, and the gap between us cannot be crossed on any human timescale. The isolation is the geometry. The isolation is the speed of light. The isolation is the simple fact that 280 kilometres of empty road, preserved at honest ratios, takes years for even the fastest signal to cross. This is our situation. 2 grains, a gap, silence, possibly full of noise we cannot hear. A hypothetical neighbour we cannot meet at a distance that our best technology cannot usefully cross in any near-term future. And beyond that nearest grain, another and another and another, scattered across a galactic room 7 million kilometres across. Each of them a potential civilization, each of them unreachable, each of them existing or not existing in a silence we cannot disturb. The grain of sand model in its final lesson is a model of patience, a model of being still and watching and listening and waiting for the occasional photon from a distant grain to arrive, carrying some small piece of information about what is happening there. That is what astronomy is. That is what our species has been doing at increasing levels of sophistication for the last 100 years. We have been watching the other grains, we have been cataloguing them, measuring their positions, studying their spectra, searching for planets, listening for signals. And the work continues. The patience continues. The scale of the emptiness has not discouraged us, it has only clarified what the work requires. Every time you pick up a grain of sand from now on, you can remember this. You are holding a star. Somewhere in the other rooms, in the other cities, in the other corners of this galactic arrangement are other grains, other stars, other potentially inhabited worlds. You will not visit any of them in your lifetime. No human being of our current era will. But they are there. They are real. They are arranged around you at honest ratios, at compressed distances, at measurable separations, and the universe is what they are arranged in. The vast, quiet model room, with grains scattered across it at intervals that take entire civilisations to think about, let alone traverse. Hold the grain, feel its smallness, and feel the enormous room it sits in, quiet, patient, waiting, full of other grains you will never meet, but that are in their own ways just as present as yours. That is the cosmos. That is the scale. That is what the model, when walked through all the way, actually teaches. Not that we are alone, not that we are surrounded. Something in between. Something that depends on the honest geometry of a universe whose defining feature is distance, whose defining structure is emptiness, whose defining sound is silence, punctuated by the occasional ancient photon arriving from an unreachable source. Part 22. Time at scale and the ancestor light. We have talked about distance at scale. We have talked about the speed of light at scale. We have talked about cosmic expansion and dark energy, and the boundaries of the observable universe. Let us spend one more stretch of time on a subtle but important feature of the model, the light we see. When you look at the grain of sand that represents Proxima Centauri at a distance of 280 kilometres in our model, the light arriving at our position left that grain more than 4 years ago. We are not seeing Proxima Centauri as it is now. We are seeing Proxima Centauri as it was 4 years ago. If something dramatic happened on that star 3 years ago, an enormous flare, a sudden brightening, a catastrophic event, we would not yet know. The news, carried by photons, has not yet had time to cross the model space between us. Extend this logic outward. Every star you see in the night sky is a time machine. The nearer stars show you the recent past. The farther stars show you the more distant past. When you look at the brightest stars in the constellation Orion, some of them are hundreds of light years away, which means the light you see left them hundreds of years ago. Those stars may have already gone supernova. We may simply not yet know. The light from the explosion has not yet had time to reach us. It is still crossing the intervening emptiness at its patient 0.2 of a millimetre per second in our compressed model, at its 300,000 kilometres per second in the real universe. Either way, still in transit, still on its way. Now extend further. Stars in our own galaxy, at distances of thousands or tens of thousands of light years, are showing you the galaxy as it was thousands or tens of thousands of years ago. Stars in Andromeda, at 2.5 million light years, are showing you Andromeda as it was before Homo sapiens existed. Galaxies in the Virgo cluster at 54 million light-years are showing you Virgo as it was during the Eocene, when the ancestors of modern mammals were beginning to diversify on Earth. Galaxies at the edge of the observable universe are showing you the cosmos as it was when it was less than 1 billion years old, long before the Sun had formed from the gas cloud that would eventually produce our solar system. Every time you look up at the sky, you are looking back through time. The stars are arranged from your perspective, not only at different distances, but at different moments in history. The night sky, properly understood, is a map of the past, a palimpsest, a layered view of the cosmos at all the different ages the light has taken to arrive. At grain of sand scale, this means that each of the grains you see in the model room is not the grain as it exists right now, it is the grain as it existed when the light left it. The grains of the local group are showing you the room as it was millions of years ago. The grains of distant galaxy clusters are showing you the room as it was tens or hundreds of millions of years ago. The grains at the cosmic horizon are showing you the room as it was billions of years ago, just after the universe first became transparent. This is what looking at the sky actually is. It is not a view of the universe as it is a view of the universe as it was. And the distribution of delays, the fact that different parts of the view correspond to different historical moments, is built into the geometry of the cosmos. You cannot see any part of the universe in the present. You can only see it with some delay, corresponding to the light travel time from that part to your eye. The present state universe is by definition invisible. Only the past is visible, only the light that has already had time to travel. Think about what this implies. The universe we observe is, in a very real sense, a reconstruction. We piece together the current state from a patchwork of images at different ages, extrapolating forward based on what we know about physical laws, because no direct view of the present is available to us. Every observation carries its own delay. Every measurement is at the moment of measurement already out of date by the light travel time from the source. There is no now in astronomy. There is only then, at many different thens, delivered to our instruments at the single moment of detection. The grain of sand model, by preserving the temporal weight of the distances, shows this directly. Every grain you see is a grain as it was. The compression of distance does not compress the ages of the photons. Those ages are real. Those ages are preserved. And when you look at the model room and imagine all the grains laid out at their various compressed positions, you have to also imagine that each grain is showing you itself from some different moment in the past, a temporal patchwork, a composite of histories, a view of the universe that has taken, in aggregate, billions of years to assemble itself into the picture your eye is currently seeing. This is, perhaps, the most profound implication of the emptiness we have been walking through. The emptiness does more than isolate us from the other grains. The emptiness also ages the light arriving from them. Every photon hitting your retina right now is a messenger from the past, carrying information about how the universe looked when the photon was emitted, not how it looks now. The universe we see is the universe delayed, the universe aged, the universe assembled from records of its own history, rather than from any direct present state view. And yet, this is not a limitation, it is a gift, because the delayed view is also a record. By looking at more distant galaxies, we look at more ancient moments in cosmic history. By studying the oldest photons, the cosmic microwave background, we study the universe as it was 380,000 years after the Big Bang. The deeper we look, the further back in time we look. The telescope is a time machine disguised as a light collector. Every instrument we build to see deeper is also an instrument to see earlier. And the combination of distance and time built into the geometry of the universe is what makes cosmological history accessible to us at all. At grain of sand scale, this combination is the most beautiful thing the model contains. The room is full of grains. The grains are not just at different distances, they are at different ages. The room is not just a spatial arrangement, the room is a temporal arrangement. The room is the universe rendered as a palimpsest of its own history, with the most distant grains showing the earliest moments, the nearest grains showing the most recent moments, and the gradient between them telling the story of everything that has happened since the photons began their journeys. Hold this. Let it settle. The grain of sand in your fingers is the sun as the sun is, or very nearly so. Any photon arriving at your eye from the grain has taken almost no time to get there, a millionth of a second at model scale. The nearest other grain is the nearest other star, as it was 4 years ago. The further grains are further back in time. The farthest grains are showing you the early universe, all of it arranged in the same room, in the same model, at the same moment of your observation. This is the universe honestly displayed, not just as a structure, but as a history, not just as a collection of distances, but as a distribution of ages. The emptiness connects the grains. The light connects the moments, and you, in the center of the room, see it all at once, across all the durations, a full view of a cosmos that has been preparing this view for you for billions of years. The sky has a great deal to say right now, and it is saying most of it in silence. The silence is the structure. And you are, for the brief moment of your life, standing at the center of it, holding a grain of sand in your fingers, looking out at a room whose walls are the cosmic microwave background, whose floor is the fabric of space-time, whose air is dark energy and vacuum, and whose scattered contents are the 2 trillion grains of sand that make up every galaxy in the observable universe. Hold the grain a while longer. Let the room settle around you. And when you put the grain down, let it be gently, because every grain is a star, and every star is one of our neighbors, and every neighbor is someone we might one day, perhaps, find a way to greet. For now, we hold, we look, we measure, we wait, and the model in its patience teaches us that waiting is most of what there is to do at honest ratios when the room is this large and the crossings are this slow and the universe is what it is. The sky has a great deal to say right now, and it is saying most of it in silence. The silence is not the failure. The silence is the structure. It is the shape of what a universe is at honest ratios when you compress it all the way down to a grain of sand. A grain of sand at the centre, and then more space than any walk can cross, scattered with other grains, separated by distances that no intuition can hold without a model to translate. Hold the grain, feel its smallness, and feel in the same gesture the enormity that surrounds it. Both are real. Both are ours. The universe is large and we are small, and the smallness does not erase us. The smallness just tells us where we are. And that is a starting point, a single grain of sand in the centre of a room, on a table, in a house, in a town, on a planet, around a star, in a galaxy, in a universe, held between finger and thumb. Real, present, ours, for now. That is the model. That is the scale. That is the universe, compressed as far as honesty allows. And that is where we live.